Unit 1-4 is dealing with postulates and theorems relating to points, lines, and planes. And what I've done is I've created a table, a little chart, to help you summarize or memorize and visualize all of these postulates in word form that are below the chart. So we're going to go below the chart first, and we're going to talk about these postulates, and then we're going to go back and create the chart from memory, we hope. A line contains at least 2 points. Now, if we think about any 2 points, through any 2 points, there's exactly one line. In reality, a line contains an infinite number of points, but it contains at least 2, and through any 2 points, there is exactly one line. Or we could say that 2 points determine one line. No matter where you put any 2 points, you can only draw one line that contains those 2 points. So by writing those 2 points, I've determined a specific line. So the blue line was determined by first placing the 2 blue points. The red line was determined by first placing the 2 red points. The green line was determined by first placing the 2 green points. So because of that concept, we say a line contains at least 2 points, and we say that through any 2 points, there's exactly one line. Now, we say that a plane, and I'm just going to remove all this line stuff when I talk about plane stuff. A plane contains at least 3 points not all in the same line. In other words, at least 3 non-collinear points. Well, let's look at that. If we had 3 points in the same line, all we determined was a line. We really didn't determine a plane. And if I draw a vertical, and you can understand better, if I drew 3 collinear points, I've determined a line, but we could draw a plane that way that hit that line. Or we could draw a plane at a little different slant. That was a very bad drawing. We could draw a line at a little bit different slant that hit that, a plane at a different slant, excuse me, that hit that line or in a different place. But if we drew 3 non-collinear points, 3 points not all in the same line, then if we were to connect that, we would get one specific flat surface. In other words, a single plane is determined by those 3 points. Okay? You couldn't draw a plane that was coming in at some different angle and hit that. All 3 of those, you see. Now, the way to draw this better, because you can see I'm struggling with getting that drawn, is to go ahead and draw a 3-dimensional object like a cube. And the way we do that is we would go ahead and make a square, and then we'd scoot over and up a little bit and make it dotted and then solid. And then we would connect and hopefully you can actually see a cube with a blue front face and a red back face and green side left and right faces. If we took these 3 points, not all in the same line, the only plane that will hit all 3 is that left face, you see. If I took these 3 points, not all in the same line, those 3 non-collinear points, there would be only one plane, one flat surface that would hit all 3 of those. So a specific flat surface or a specific plane is determined by 3 points not all in the same line. And so we would say that through any 3 non-collinear points, there is exactly one plane. Through any 3 points, there's at least one plane. If I had 3 collinear points like that, the top plane would hit it, the right plane would hit it. I could also draw a diagonal plane that hit it. An infinite number of planes would hit it if the 3 points were collinear. But if the 3 points are non-collinear, then exactly one plane hits it. And so we could say that a plane is determined by 3 non-collinear points. So a line is determined by 2 points. A plane is determined by 3 points, not all in the same line, or 3 non-collinear points. If we wanted to determine 3 dimensions, and let's talk about that. One point has an infinite number of lines that go through it. Remember, a line has length, which is 1 dimension. So if I take 2 points, then I've determined a line which is 1 dimension. So 1 dimension or a line is determined by 2 points. Now if I take a third point not on that same line, then I've determined a specific flat surface. And so we say that a plane is determined by 3 points not on the same line, or 3 non-collinear points. Now if I wanted to determine 3 dimensions, you see, because a plane is really 2 dimensions, right? A bunch of little square units. If I wanted to determine a third dimension, then I would have to have 4 points not all on the same plane. So I would have to get away from that plane, and then that would create the third dimension, okay? So if I took a fourth point not all in the same plane as those, then it would take a 3-dimensional object to hit all 4 of those points. So we say that space, 3 dimensions, is determined by 4 points not all in the same plane, okay? So let's kind of review these a little bit. A line contains at least 2 points. A plane contains at least 3 points not all in the same line, or 3 non-collinear points. Space contains at least 4 points, not all in the same plane. When we talk about a line, we're talking about 1 dimension length. When we're talking about a plane, we're talking about 2 dimensions, length and width. When we talk about space, we're talking about 3 dimensions, length, width, height. Through any 2 points, there is exactly 1 line. Through any 3 points, there's at least 1 plane, but if they're non-collinear, then a plane is determined. Through any 3 non-collinear points, there is exactly 1 plane. If 2 points are in a plane, then the line that contains those points is also in that plane. If we have a flat surface, a plane with 2 points in it, then the line that contains those 2 points will also be in it. If 2 lines intersect, exactly one plane contains them, and you can see that those points would be non-collinear points, but they're all still in the same flat surface, and so they're coplanar but not collinear. So if two lines intersect, then exactly one plane contains them. Given a line and a point not on that line, what did we just create? Non-collinear points. If we have non-collinear points, we have a single flat surface that hits them all, right? All right, let's summarize all of that information in this little chart. The type and number of points. 1 point. If we have 1 point in space, how many lines could we draw that contains that 1 point? Well, an infinite number. How many planes? Well, we could consider that every one of those little cuts we made was being made by a flat surface. And so 1 point could have an infinite number of planes going through it. Remember that a line is determined by 2 points, not 1. A plane is determined by 3 non-collinear points, not 1. Space is determined by 4 non-coplanar points. So space has not been determined. So there's really not infinite space. We just say that space really is not been determined yet. So we're going to say kind of empty set on space. There is an infinite number of lines that go through 1 point. There's an infinite number of planes that go through 1 point. Space is 3 dimensions, and 1 point has not yet created 3 dimensions. A point has no dimensions. In fact, remember, a point was a what? It was an undefined term. It has no size or shape. It's a location. And the symbol for a point is PT if we were just going to name a point. But what we're trying to talk about is, have we created any dimensions yet? No. And so there's not a symbol to represent no dimensions. Now, if we take 2 points, then we've then determined exactly 1 line. There's an infinite number of planes from all directions that you could run through that. Space has not yet been determined. This object we've created is 1 dimension length, you see. So now we have created 1 dimension. That dimension we've created we call length. And if it was in inches, we would say inches to the first power, or feet to the first power, or centimeters to the first power. And we would have just a 1-dimensional object, and the 1 or the first powers understood. Now, when we take 3 non-collinear points, or 3 collinear points, excuse me, the very definition of collinear says we're still in a line, so we still have 1 line. It takes non-collinear to get a plane, so we still have no plane determined, so there's still an infinite set that would hit it. Space has not yet been created because we're still dealing with 1 dimension, so we still have 1 dimension length, which again is measured in inches to the first, or feet to the first, or centimeters to the first, and the visual is just an object with length. Once we get non-collinear, then obviously we have no line anymore. But 3 non-collinear points determine 1 plane. We've not yet determined space. A plane would look like this, created by 3 non-collinear points. If we actually join the 3 points, we'd get a triangle, but we're thinking about one flat surface that would hit all three. Notice that that has two dimensions, length and width. So now we have a two-dimensional object. It has the dimension length, and it had another dimension width. The unit of measures like square inches or square feet or square centimeters, and the visual aid would be how many of these little guys are there that it takes to fill in the figure. So we're talking about square units versus one-dimensional units, okay? Now, if we have three non-collinear points that are still coplanar, we still have the same scenario. Okay? I'll go ahead and write it all in. We still have two dimensions. They are still length and width, measured in square inches or square feet or square centimeters, etc. And the visual aid is still how many little square units are there. When we take four non-coplanar points, we now have determined space. If they're non-collinear or non-coplanar, there's not one line that'll hit them all. There's not one plane that'll hit them all because they're non-coplanar. But we have determined space, which is three dimensions, and the dimensions are length, width, and height. And we measure three dimensions in cubic units. Now, what we usually measure in centimeters or inches or feet is perimeter, right? Length or perimeter. And we would measure in square inches, square feet, square centimeters, area. And when we're dealing with cubic units, then we're dealing with volume, right? So perimeter is measured in inches, feet, centimeters, one dimension. Area is measured in square inches, square feet, square centimeters, two dimensions. Volume is measured in cubic inches, cubic feet, cubic centimeters, or cc's, cubic units, okay? Any questions on Unit 1.4? So you need to study the postulates, and then the chart's kind of a summary of those. You may take this information that we're looking at over here with the units of measure and turn in the Algebra 1 text to page 174A and see how the little scaling up and down relates to that. You can also turn to the very last section of the geometry book, which is dealing with the same thing that's on page 174A of the algebra book. Actually, let me find it for you. It's actually page 301 of this geometry text. So page 301 of this geometry text and page 174A of the Algebra 1 text are using this information on perimeter, area, and volume and the concept of 1, 2, and 3 dimensions to learn how to scale up or scale down when you're dealing with units of measure.